Good morning, everyone. I'm going to start where we left off in the last lecture. We had talked about encoding the Turing machine so that we can pass one Turing machine to some other Turing machine. So, given a Turing machine M, if there is a Turing machine M, it can accept certain words. We were going to check that if WI was encoding of Turing machine MI. So, can this Turing machine also accept WI or not? Can a Turing machine accept a Turing machine's encoding as well as the word that it takes as an input? The next question we asked ourselves was that if there is a Turing machine called M1, and let's say that W1 is the encoding of M1. So can a Turing machine accept the encoding of itself or not? Okay, so this is a problem that we are trying to solve, and we will be using the notion of algorithms. Who is disturbing my class? Why are the people so late? Okay, so we had done, so this is how we had encoded the machine. If you remember, you would encode it like in 00001 and use the respective I, J, and K values. And you had assumed it to be a binary representation, but it can be generalized for other alphabet also. And we finally figured out that this is the Turing machine encoding. So this is a Turing machine encoding, and so if I pass this entire string to M itself, this is the encoding of M, and if I want to pass this to the Turing machine itself, whether it accepts or not, that we are going to talk about. We defined a diagonalization language which says that a Turing machine M0 will accept some strings of length, some machines M0, M1, M2, whatever the machines are possible, we have encoded them. So this row represents that what are the machines that it accepts. Suppose it accepts machine 1, then we can put a 1 over here, and suppose if it does not accept machine 2, we can put a 0 here. Suppose if it accepts machine 7, say, then we can put a 1 here, so on and so forth. So we had a specific question in mind about the problem of diagonalization, which meant that if the machine accepted itself, so on the diagonal you will get the encoding of the machine. So we had to solve this problem. So we are saying over here that the coding, just a second. Previous coding of Turing machines allowed a concrete notion of MI, the ith Turing machine, which is TM, whose code is WI. So if you're talking about Turing machine MI, then the encoding of this Turing machine is WI, which is the ith binary string. And if we find that WI is not a valid code, then TM will have one state and no transition, and it will halt immediately on any input. The other thing that we have is that we have a list of TMs in certain order with a one-to-one mapping between TMs and MI and WI, which is their respective encoding. So the diagonalization language LD is the set of strings WI. Excuse me. Okay. Diagonalization language LD is the set of strings wi, that is those encodings of machine Turing machines such that wi is not in lmi, language of mi, that is this encoding is not in the language of the Turing machine, that is this Turing machine does not accept this string, that is the diagonalization language. So specifically we are talking about what lies on the diagonal. LD consists of all strings W such that the TMM whose code is W does not accept W. All those Turing machines who do not accept their own encoding are a part of LD. So here, see, I'm not saying that there is no Turing machine that does not accept its code. I am not saying anything about that. I'm only saying one thing, that in the diagonalization language, it will contain set of all words WIs which are not accepted by their respective MIs. That's all I am saying. So that thing you have to be careful about, that what we are saying and what we are not saying. We are not saying a lot of things over here. So you just need to focus what we are saying. And when we are not saying a certain set of things, that is what are the that is that if there is a Turing machine that accepts itself, if we are not saying that thing, that doesn't mean that it is not true. For now, we will focus that the diagonalization is a set of words which are the encoding of Turing machine, ith Turing machine, such that that particular encoding is not the part of the language this Turing machine accepts. So basically, a Turing machine MI will accept certain kinds of words. You know, suppose if I say A plus B star, so it is going to accept a plus or 0 plus 1 star. So if there is a Turing machine 0 plus which is accepting this set 0 plus 1 star, in that case it is accepting all possible combinations of zeros and ones. So it is accepting string 0 1, it is accepting 1 0 1 1 1 0 and so on and so forth. So it is accepting different kinds of words, but my focus is on the word WI, which represents the specific encoding of this Turing machine. So this kind of a word, whether it accepts. So incidentally, the example I have taken, this also belongs to the language 0 plus 1 star. So in this case, this is being accepted by my new Turing machine that I have just defined. But what if this Turing machine only accepted the language 00 and 01? Let's assume that it only accepted two words. Then definitely this encoding would not have been accepted by this new machine that I have defined. So we have to find all those sets which do not accept their own encoding. So in this case, this kind of a Turing machine will accept its own encoding. But in this scenario, this kind of a Turing machine will not accept its own encoding. So my focus is to find all those Turing machines that do not accept its own encoding. And we are not yet talking about the machines that actually do. Okay, I hope that the diagonalization language is clear to you. Otherwise, things will start to get confusing from now on. If you have a question, you can please ask me. Okay, I am assuming that the diagonalization language is now clear. So it is simply the set of all words or all encodings of Turing machines such that that particular encoding is not accepted by the Turing in question. So we are saying that first Turing machine, whether it can accept the first Turing machine or not, so on and so forth. So zero by zeros and ones, you represent that, one means that yes, it is going to accept, and zeros means it is not going to accept. So if you take the diagonal, there will be certain things where this will be zero, that not going to accept, and in certain things it may not be zero. Now the question is how to encode such a word. So suppose okay, so one means that mi accepts wi, and 0 means mi does not accept wi. So if you look at this character vector, this means this is a characteristic vector of Turing machine 1. It does not accept itself, but it accepts this encoding, it accepts this encoding, it accepts this, and so on and so forth. So this is the characteristic vector, but what we are concerned is what lies on the diagonal. So 1 means that mi accepts wi, and 0 means mi does not accept wi. All any one in the row indicates that the corresponding string is in the language. So to construct a diagonalization language, now you have to find the words that are in the language. Okay, so words are typically of this form. And remember when we had returned that what was the first word, we had done something like this, that write a 1w. So if you had nothing, epsilon was the first word, and then if you had 0, this was the second word, so on and so forth. So it is difficult to find the number of words in the diagonalization language if you go this way, reading of all, because this could be any number of Turing machines in question. And so what we generally, the way we read off is like this. So to read this matrix, the typical idea is to say that this is the first word, then this is the second thing, then the third thing. This is how we read. Instead of going row wise, we go this way. So to find which possible word it is, you simply you will, when you will see that if you complement the diagonal, you will get the corresponding string. So just complement the diagonal to collect the corresponding string of this form. If you will complement the diagonal, you will get the corresponding string, which is representing that particular language. So this is called the technique of diagonalization, and we will be now proving using this technique that diagonalization language is not recursively enumerable. Going back to my definition, I don't know if you remember or not, but I would still want you to revise these concepts. There are a lot of things we have talked about, some things that are recursive. Then we have talked about some things that are recursively enumerable. So if you remember the difference between recursive and recursively enumerable, can you help me with them? What is the difference between recursive and recursively enumerable? Can anyone answer this question? What is the difference between recursive and recursively enumerable? No one? We had a lot of discussions about it. Don't know, Chirag. How is it possible? I discussed it in the last class.
याद नहीं.
Not studying. This is important. I mean, this is पूरा talk ही हमने इस concept तक पहुंचने के लिए पढ़ा है. Frankly speaking, this is where it all ends. So everyone has to at least please start studying, people. Anyone who can help me? Any of the girls who can help me? Because last time somebody did answer this question. It is related to acceptance and rejection and all those things. That is the hint.
मैम रिकर्सिवली इन्यूमरेबल लैंग्वेज होता है द मशीन हॉल्ट फॉर इनपुट स्ट्रिंग विच आर इन लैंग्वेज एल. और मैम
Okay,
रिकर्सिव लैंग्वेज होता है इट ऑलवेज हॉल्ट वेदर इट इज एक्सेप्टेड बाय द मशीन और नॉट.
great. Thank you so much. You are right. So, uh, that was Santosh, I guess. है ना? संतोष बोल रहा था ना? Okay.
Yes, ma'am.
So, thank you. Thank you so much, Santosh. You are right. Recursive means that no matter what the input is, if that input is accepted by the machine, it will be accepted and it will halt. Suppose that input does not belong to this language, then it will be rejected and also it will halt. So, such languages where you always have a decision and you always halt, whether it is accept or reject, those are recursive languages. Please be very clear about this. And all those languages where you have a decision on accept, I'm drawing this here. You have decision in accept, on accept, and you halt. That is, if a word belongs to the language, it will accept and it will always halt. But if it does not belong to the language, I have no idea what it is going to do. Whether it's going to halt or loop forever. You know, some in something, some states we don't know that what happens if the word does not belong, so that means that you cannot reach a decision. So recursive languages always give you a decision, and recursively enumerable languages always tell you that if something belongs to that language, if a word or a string belongs to that language, then it is going to accept and halt. But if it does not, then you can't say anything about it. So most of the places it is written that it is going to loop forever, but I generally put it differently. I say that it may loop forever, it may halt at some time, but I will never get to know, because suppose if I stop at this moment, okay, now this is not halting, let's assume that the word is rejected, maybe in the next state it could have been rejected. So what is going to happen? So mostly when we design the Turing machines for such languages, we don't have a reject state only. We generally don't make a reject state only. So any language, recursive language, that is, there is a decision of, halting on accept and reject. If you want to convert it to recursively enumerable, simply halt here and drop off this reject state and make it somehow loop forever. It will become recursively enumerable. So please just remember this. I hope this is clear. So the recursive languages are those where if a string is being accepted by the machine, then it accepts it and halts. It is a halt state. If it is not being accepted, it does not belong, then it will get rejected and it will halt. So you always have a decision for recursive cases. For recursively enumerable, you will always accept and halt for the word that belongs to the language, but you may not halt ever. You may loop in forever in case there is a word or a string, there is a string that does not belong to the language and it has been passed to the Turing machine. So to convert a recursive thing into into recursively enumerable, you simply have to drop off the reject state and let it loop forever, and you have your recursively enumerable version. So now we are going to prove that LD is not even RE. It is not even recursively enumerable. So we have already talked about regular languages. Then we have all talked about your CFGs. We have dropped off something in between. Then we have talked about, sorry for my bad drawing. We have talked about recursive, and then we have talked about recursively enumerable. Okay. And we have said that those do that we don't know what is going to happen if the word does not belong to the language. We have talked till here. Now we are saying that this LD is not even recursively enumerable. So it lies, somewhere outside this set. So This is another bigger set. So this is not even RE. This is not even recursively anywhere. This is somewhere your LD lies. Okay, this is what we have to prove. So basically, what we are showing with this, what we are going to show is that there are some problems that are not solvable, not decidable for any given input, and they are not solvable. We will, if we can map those problems to LD, we, you know, there you will in algorithms, आप पता नहीं NP completeness पढ़े हो कि नहीं, but algorithms में आपने अभी तक वो सारी problem solve करी हैं जो solvable है. तो algorithms are basically all the languages that are recursive, because for example, if I pass a number and ask you to find whether it is even or odd, then you will say ki okay, you have an answer. So that is an algorithm. So it is recursive. You have a decision. Sorting कर रहे हो, you have a decision. आप अगर edges Kruskal algorithm लगा रहे हो, Prim's algorithm लगा रहे हो, solvable. अब मैं अगर बोलूं कि आप के पास लेट मी टेक एन एग्जांपल कि ओके, आप अगर कोई कोई क्रिप्टोग्राफिक एल्गोरिथम लगा रहे हो, तो आप उसको एनकोडिंग तो कर सकते हो, बट विदाउट यूजिंग ब्रूट फोर्स आप क्या उसकी डिकोडिंग कर सकते हो? तो देयर आई माइट नॉट हैव एन आंसर. So we are basically saying that there will be certain problems that have not been solved in computer science till now, and all those languages we put in that box, in that particular circle. So the idea is that if I could find one language which was not even recursively enumerable, and if I map those problems to, you know, look like this diagonalization language, so because they look like this diagonalization language, then we can say that okay, because it looks like this, then that is also not decidable or solvable. So that is the whole idea of Turing machine. If you remember, in my very first class, I talked to you about acceptance and decision, but I also talked about something that whether some problem is computable or not. We had talked about that also. So this is where we are getting into. We have, for now, we have talked about how the things are solvable. Whether, see, we are not here focusing on, you know, efficiency and all that. We are making very crude and very simplistic machines, if you say they are very rough, but we are solving problems. Now the problem is that there still exists a lot of problems that are not solvable by computers. For that we need a category, and we have that right now. So to construct LD, you just need to complement the diagonal, correct the corresponding things, and we are going to use this diagonalization technique to prove that LD is not in RE. Okay, just a second. So we are saying that the complement diagonals will disagree in some column. In some columns, we will not be able to decide whether the Turing machine accepts itself or it does not accept itself. It was the chicken and egg paradox that I told you in the last class, where I discussed about कि okay, long वाला word है, फिर French वाला word है, and फिर हमने एक heterological word लिया था. So in that case, हमने बोला था कि long is not a long word, so long is also not a French word. So, but long was heterological in the sense कि long खुद में वैसे एक short word है, but जो चीजें long language में है, मतलब वो सारी लंबी हैं, तो वो सारी चीजें, मतलब it is holding those things which are just exactly opposite of what it represents itself. So that's why it was heterological. Similarly, French is, I don't think, a long word. and let me categorize it at 0. French is not a French word, it is an English word, but it is heterological in the sense that French holds all the French dictionary words, but if you use the word French itself, it does not mean it is itself not French, so heterological. Then heterological is a long word, yes, it is not a French word, but now we got stuck here. We said that, okay, if I say heterological is a heterological word. Heterological word means something jo what it is saying, whatever its definition is saying, it itself doesn't mean that thing. So if heterological belongs to this set, if it is one, if you put a one over here, then we will say that heterological doesn't mean itself. But इसका meaning तो by definition उल्टा ही था ना कि it is saying that it doesn't. Heterological definition is that all the words that do not mean what they actually signify. So that means if I put a one here, that means the heterological does not mean what it means. But definition तो दी हुई है ना, तो contradiction. So I cannot put a one here. But what if I try to put a zero? That means heterological doesn't mean what it means. Then it should have been a part of this language. Then it should have been a part of this set. So again zero पे भी contradiction. तो डायगोनलाइजेशन लैंग्वेज भी ये कह रही है कि जब आप M1 M2 M3 के लिए बनाने वाले हो इतना ये मैट्रिक्स, और यहाँ पे भी आप M1 जो स्ट्रिंग्स हैं ये ट्यूरिंग मशीन्स की एनकोडिंग है, ये पास करने वाले हो. So we are not saying that things will not be one here or here, but at some point of time there will be a Turing machine which will land you in this situation. So the complemented diagonal will disagree in some column with every row. Therefore, it cannot be a characteristic vector of any Tn. So any non-zero element at the location I, comma I in the complemented diagonal means mi does not accept. So अगर आपने यहाँ पे अगर आप notice करो, यहाँ पे ये है. अब अगर आपने यहाँ पे फॉर एग्जाम्पल इसी को देख लो, ये जीरो था मतलब एप्सिलॉन है, तो एप्सिलॉन का ट्यूरिंग मशीन है. हमने अभी भी बात करी थी जो ट्रिवियल केसेस है, इफ इट इज नॉट द राइट एनकोडिंग वी आर गोइंग टू हॉल्ट. सो अब आप इसको अगर कॉम्प्लीमेंट करोगे तो ये कुछ ऐसा बन जाएगा 1 0 0 and so on and so on and someone. So यहाँ पे जैसे आप इसको वन करते हो ये कॉम्प्लीमेंट्री डायरेक्ट डायगोनल आ गया, उसकी रिप्रेजेंटेशन आ गई. तो वो ये बोल रहा है कि at it means that mi does not accept whenever you get a non-zero by complementing, it does not accept the corresponding wi, but there is a situation where it means exactly the opposite. So then when it is going to land up in that situation, then we can say that because there are some strings that are of this situation, we will say that this problem is not recursively enumerable. Let's see how we do that. I know it is a bit confusing, but let's see how we do that. मम्मा बहुत अच्छा बना था. Okay, thank you. Okay, so LD is not a recursive language. That is, there is no TM that accepts LD. There is not a recursive. Sorry, it's not a recursively enumerable language. Matlab, there is no TM that you cannot build a Turing machine that accepts LD. How are we going to prove? So let there be a Turing machine because LD is itself a language. It contains all those set of Turing machines, all those words where M, WI ये वाली encoding पड़ी है. MI, WI. So let's say MN, WN. सिर्फ ये मान के चलते हैं कि मान लो LD में सिर्फ 2 एलिमेंट्स हैं, मतलब वो ट्यूरिंग मशीन्स जो ट्यूरिंग मशीन्स हैं और उनकी खुद की एनकोडिंग, जो हमने अभी एनकोडिंग की थी, WI इज देयर एनकोडिंग. सो व्हेन आई पास उनके खुद की एनकोडिंग टू दिस मशीन, इट इज नॉट एक्सेप्टेड. सो लेट LD contain only those combinations which are not accepting themselves. So now, because this is a language, that means I can define a Turing machine for it. Let's assume that I can define a Turing machine for LD. LD क्या है? लैंग्वेज है, मतलब कुछ सेट ऑफ वर्ड्स एक्सेप्ट कर रहा है. इस केस में ये वाले सेट ऑफ वर्ड्स है उसमें. Now let me design a Turing machine for this. So if M is one of the Turing machines in the Turing machine list previously, MI, now let's see if the corresponding WI is in LD. So मान लो, वापस से मैं ये बनाती हूँ, MI was in LD, मतलब कोई आयत ट्यूरिंग मशीन थी जो अपनी एनकोडिंग एक्सेप्ट नहीं कर रही थी. और लेट्स से कि मतलब बेसिकली सेट एम्प्टी नहीं था, मैं ये कहना चाह रही हूँ. एंड लेट्स से देयर वाज सम nth ट्यूरिंग मशीन आल्सो जो अपनी एनकोडिंग एक्सेप्ट नहीं कर रहा था. Now, let's say that a word belongs to LD. This is a word that belongs to LD. इसका मतलब कि जो हमने ट्यूरिंग मशीन बनाई है M, which is accepting LD. So, अगर MI accepts WI, मतलब बेसिकली ये वाला जो वर्ड है वो M एक्सेप्ट कर रहा है, बट because of the definition of LD, we say that WI cannot be accepted by MI. ये समझ आया? Now is the time to ask questions if you are listening. Yes, please. बोलो बोलो बोलो.
मैम एक बार और रिपीट कर दो ये पार्ट.
थैंक यू सो मच, क्योंकि आप मेरे को रिपीट करने को बोल रहे हो, इसका मतलब आप सुन रहे हो. सो okay, going back. We are going to prove that LD is not recursively enumerable. That is, we are going to prove that there will not be any Turing machine that will accept it. So we are saying that let M be the Turing machine and let the language of M be LD, the diagonalization language, which I have just defined above, that these are the words that will be accepted. So M is one of the TMs in the list mentioned previously. मतलब कि LD, अब जो M है वो अपनी खुद की एनकोडिंग एक्सेप्ट कर सकता है. So we are going to check if its corresponding word, अब LD की खुद की रिप्रेजेंटेशन एक्सेप्ट हो रही है कि नहीं हो रही. देखो, अगर LD के अंदर कोई वर्ड्स एक्सेप्ट हो रहे हैं, like LD this machine, then M is one of the TMs in the Turing machine list that you had mentioned. LD एक Turing machine है, तो इसका मतलब LD खुद को एक्सेप्ट कर पा रही है. हम ये एज्यूम कर रहे हैं, अभी हमारी एजम्पशन है कि हम ये एज्यूम कर रहे हैं कि हमारे पास एक mth ट्यूरिंग मशीन है डायगोनलाइजेशन लैंग्वेज की. अब if that is possible, then M is one of the TMs that have been mentioned in this list. यहाँ पे कोई एक TM होगी, यहाँ कहीं होगी LD के लिए एंट्री, यहाँ कोई LD के लिए एंट्री होगी. इधर बहुत सारी ट्यूरिंग मशीन्स आगे होंगी, या इधर देख लो, यहाँ कोई LD के लिए एंट्री होगी इधर कहीं डायगोनलाइजेशन पे. तो जैसे M1 M2 M3 है, वैसे ही जो मैंने अभी ट्यूरिंग मशीन बनाई है M फॉर LD, उसकी एंट्री भी यहाँ कहीं होगी. सिंपल M लिख देती हूँ, जो यहाँ पे लैंड अप करेगी. इसका मतलब कि हम ये बोल रहे हैं कि इसके जो वर्ड्स हैं, क्योंकि हमने ट्यूरिंग मशीन बनाई है, तो कुछ वर्ड्स ये एक्सेप्ट कर पाएगी. So this is what it is saying now. So Now, if we have to check whether this encoding of this machine itself, W is I is the encoding of M itself, which is the Turing machine that accepts LD. Now we want to check whether this corresponding word is, अगर इसकी ट्यूरिंग मशीन है तो कोई वर्ड तो होगा ना, तो वही हम बोल रहे हैं कि इसकी ट्यूरिंग मशीन है तो उसका कोई वर्ड होगा और उसकी एंट्री यहाँ पे हुई होगी. सो अगर वो वर्ड एलडी को बिलोंग करता है, अगर वो वर्ड एलडी को बिलोंग करता है, इसका मतलब जो मैंने अभी नई ट्यूरिंग मशीन बनाई है वो जो है उस वर्ड को एक्सेप्ट करती है. मैंने ट्यूरिंग मशीन बना दी है जो एलडी के सारे वर्ड्स को बिलोंग करती है और जो भी वर्ड मैंने पिक किया वो ये वाली ट्यूरिंग मशीन एक्सेप्ट करती है. बट एलडी क्या था? एलडी तो वो लैंग्वेज थी जो इन एनकोडिंग्स और ये वाली ट्यूरिंग मशीन्स को बाय डेफिनेशन हम उल्टा कह रहे थे. हमने यहाँ डब्ल्यू आई को एलडी के एनकोडिंग लिया और हमने बोला कि वो इस लैंग्वेज का पार्ट होना चाहिए, ये हमने एज्यूम किया. बट बाय डेफिनेशन एलडी बोल रही है कि मैं जो है सिर्फ वही वर्ड्स अपने पास रख रही हूँ जिनकी एनकोडिंग उनकी अपनी ट्यूरिंग मशीन एक्सेप्ट नहीं करती. लेकिन यहाँ हम अपनी एनकोडिंग वाली ट्यूरिंग मशीन को खुद एक्सेप्ट कर रहे हैं. सो इट इज अ कॉन्ट्राडिक्शन. नाउ इज दिस क्लियर? इतना करेंगे, नेक्स्ट नहीं करेंगे.
हाँ मैम, ये क्लियर है.
Thank you. Anyone who needs to ask this because people get confused. Okay, I will still repeat it once again because I am not very satisfied if you have understood. I am simply saying that LD contains some list of words, and those words are those where there is some ith Turing machine. जिस I notation नहीं लेती हूँ मैं. Let me take some Turing machine जिसकी अपनी एनकोडिंग को एक्सेप्ट नहीं कर रही है. बहुत सारे ऐसे वर्ड्स हैं इसके अंदर जो अपनी ट्यूरिंग मशीन को एक्सेप्ट नहीं कर रहे. अब हम बोल रहे हैं कि चलो मान के चलते हैं कि इस लैंग्वेज को भी एक्सेप्ट करने वाली एक ट्यूरिंग मशीन है. ओके, तो लेट मी कॉल दिस ट्यूरिंग मशीन एम आई. अब इस ट्यूरिंग मशीन को जब एम आई किया तो इसमें एक वर्ड है डब्ल्यू आई एंड लेट दिस बी एन एनकोडिंग ऑफ दिस ट्यूरिंग मशीन. बट अगर वो इसका वर्ड है तो इस ट्यूरिंग मशीन एम आई को ये वर्ड एक्सेप्ट कर लेना चाहिए. ओके, तो करवा देते हैं वर्ड एक्सेप्ट. लेकिन अगर वो इसको एक्सेप्ट कर रहा है क्योंकि डब्ल्यू आई बिलोंग्स टू एल डी हमने इस कंडीशन के लिए करा है, दैट्स व्हाई वी आर सेइंग दैट दिस ट्यूरिंग मशीन शुड एक्सेप्ट दिस वर्ड. बट if this word belongs to this language, then this should not be a part of this, because by diagonalization ki language it says that I am going to only keep the words which whose encoding their own Turing machines cannot accept. So here you have got a contradiction. See, this is a chicken and egg story that I started with this lecture with. It's a paradox कि जो चीज बोल रहे हो वो लैंग्वेज खुद नहीं कर पा रही. अब हम ये बोल रहे हैं कि डब्ल्यू आई एल डी का पार्ट नहीं है, मतलब डायगोनाइजेशन लैंग्वेज का पार्ट नहीं है. इसका मतलब डब्ल्यू आई अपनी ट्यूरिंग इस ट्यूरिंग मशीन डब्ल्यू आई एनकोडिंग है. ओके, डब्ल्यू आई इज एन एनकोडिंग, सो इट इज नॉट एक्सेप्टेड बाय एम आई. सो because it is not accepted by MI and we had defined LD to be those that all those languages which were not accepted by Turing machine, that means WI should belong to LD क्योंकि डेफिनेशन ये बोल रही है. हमने बोला कि जो एनकोडिंग है वो एलडी का पार्ट नहीं है. एलडी का पार्ट नहीं है मतलब कि जो ट्यूरिंग मशीन एम है उसकी एन जो डब्ल्यू आई है वो एलडी का पार्ट नहीं है. मतलब देयर इज अ ट्यूरिंग मशीन that cannot accept the encoding of itself. So that means because of this definition हमने एलडी की तो डेफिनेशन ही ये ली है ना कि जो भी ट्यूरिंग मशीन अपने आप को एक्सेप्ट नहीं करेंगी वो मेरा पार्ट बनेगी. तो इसका मतलब कि हमारी ये assumption भी गलत है. इसका मतलब तो डब्ल्यू आई को एलडी का पार्ट होना चाहिए. सो अगेन अ कॉन्ट्रडिक्शन. That's why there is no Turing machine that can accept this language, or we cannot build a Turing machine for this language. So there is no TM that accepts LD. Now, is this okay? If you have been listening, then it will be okay. I can explain this second portion once again if you want, otherwise, I will move. Okay, so I am assuming that this was clear. Okay, so again, that's what we have learned. RE are those that are accepted or recognized by the Turing machine. Recursively enumerable की पहली बात है recursive language जो हमेशा halt करेंगी. So we are saying that simply यही बोल रहे हैं कि recursive is a subset of recursively enumerable. So we are saying that RE languages are accepted by Turing machine. Rejection की बात नहीं हुई. Rejection की बात सिर्फ इसमें होगी. Accept as well as reject, and here only accept. So each language L in this class has a Turing machine. इसको आप एल्गोरिथम कह सकते हो क्योंकि डिसीजन ले रहे हो. And it not only accepts strings of L but also tells us what strings are not in L by halting on reject state. अब रिकर्सिवली एन्यूमरेबल जो है वो रिकर्सिव नहीं होती हैं. ये एल्गोरिथम भी नहीं कहलाती है क्योंकि जब इनपुट नहीं होता उस लैंग्वेज का पार्ट तो ये आपको डिसीजन नहीं दे पाएंगे. So they accept strings of L but may not halt. Please don't write that it will loop forever in your exam. Write it may not halt. These are two different things. So that's why I'm stressing that you write may not halt when a given input string is not in L. Okay, so these are two classes we have studied. So again, same cheez repeat करें. If W belongs to L, then N accepts and halts. And if the W does not belong to L, then it eventually halts and rejects. And we call this type of Turing machine as an algorithm. So now we have introduced the notion of algorithms over here. So any given language is regarded as a problem. It is called decidable if L is a recursive language and undecidable if not. मतलब चाहे वो recursively enumerable हो या not RE भी हो, वो undecidable की कैटेगरी में चला जाएगा. अगर वो डिसाइडेबल है, इसका मतलब कि वो रिकर्सिव है. तो इस प्रॉब्लम को आप डिसाइडेबल बोलोगे या सॉल्वेबल बोलोगे. The existence or non-existence of an algorithm to solve a problem is more important than existence or non-existence of a Turing machine. मतलब अगर आपके पास ऐसी ट्यूरिंग मशीन आप बना सकते हो जहाँ पे एक्सेप्टेंस या रिजेक्शन की बात कर सकते हो, वो ज्यादा इंपॉर्टेंट है क्योंकि आप बता रहे हो कि आप डिसाइड कर पा रहे हो प्रॉब्लम डिसाइडेबल है. एंड इट इज मोर इम्पॉर्टेंट to prove whether a Turing machine it is more important as compared to proving whether a Turing machine exists to solve the problem. So इसका मतलब यह है कि ट्यूरिंग मशीन तो आप रिकर्सिवली एन्यूमरेबल के लिए भी बना सकते थे, लेकिन डिसीजन आप सिर्फ रिकर्सिव के लिए कर सकते हो. तो इसलिए ये ज्यादा इंपॉर्टेंट है ये बता पाना. तो जो भी रिकर्सिव लैंग्वेजेस हैं उनको आप डिसाइडेबल कहोगे क्योंकि वो प्रॉब्लम्स जो है हॉल्ट करेंगी या तो एक्सेप्ट में या रिजेक्ट में. इज इट ओके? I think this we have already done. Recursive language is L. There's a TM halts with L as input. It could have halted on accept or it could have halted on reject. So this is what we have studied. Recursive, recursively enumerable but not recursive, which is okay, and which is not RE also. So LD is not RE, लेकिन उसका prime LD prime is RE. LU is universal Turing machine that I will introduce. NEB में अभी introduce करूँगी. LU का prime is here and LNE ka prime is over here. So these are the relationships among three kinds of languages. We will be talking about this because we will be talking about this notion of this will be introduced. You know that LD ka prime is sorry complement is basically all those Turing machines that actually accept their encoding. So and LU is universal Turing machine that I'm going to introduce just now. So yeah, LU is the universal language, and we will be proving that it is not recursive. Rather, it is recursively enumerable. We will be using complements of recursive and recursively enumerable languages to tool is we will be using complements to prove whether they are recursive or recursively enumerable, and we will also show that recursive language is closed under complementation. पहले तो एग्जाम्स में ये थ्योरम्स एज इट इज आ जाते थे, अभी आगे क्या होने वाला है आई डोंट नो. सो स्टिल वी लेट्स हो सकता है इसकी एप्लीकेशन आ जाए, मैपिंग आ जाए, आई डोंट नो, वी विल हैव टू सी. So just read these concepts. ध्यान से पढ़ो. Okay, so complements of recursive and recursively enumerable language. If a language L is recursive, then its complement is also recursive. तो सिंपल सी बात है, अगर M है तो वो एक्सेप्ट कराता है या रिजेक्ट कराता है. अगर आप एक्सेप्ट वाले स्टेट्स को अगर आप ट्रांजिशन रिवर्स कर दोगे, जो आपने उल्टा किया था कॉम्प्लीमेंट के लिए, आपने डीएफएस में भी ऐसे ही किया था ना, सबके ट्रांजिशंस आपने उल्टे कर दिए थे, एक्सेप्ट को रिजेक्ट बना दिया था, रिजेक्ट को एक्सेप्ट बना दिया था. तो वही यहाँ पे कर रहे हैं कि एम प्राइम मतलब जो कि एल प्राइम को एक्सेप्ट करता है, वो कैसे करना है, रिजेक्ट वाली स्टेट्स अब एक्सेप्ट बन जाएंगे, एक्सेप्ट वाली रिजेक्ट. तो ट्यूरिंग मशीन, उसी ट्यूरिंग मशीन में स्टेट्स को उल्टा अगर आप कर दोगे तो आप एल प्राइम को एक्सेप्ट करा सकते हो, एंड यू कैन प्रिंट क्रिएट एम प्राइम विच दिस विल आल्सो हॉल्ट ऑलवेज. It will either halt on accept or on its reject. So that's why it will also be recursively enumerable. So कैसे बनाना है, इस प्रोसीजर लिखा हुआ है, ऑलरेडी डिस्कस कर लिया मैंने, बट स्टिल एक्सेप्टिंग स्टेट्स को नॉन एक्सेप्टिंग बना दो, उनका कोई ट्रांजिशन नहीं होगा, बाहर कोई ट्रांजिशन नहीं होगा, ये हॉल्ट रहेंगी जैसे पहले थी. न्यू एक्सेप्टिंग स्टेट बनाओ आर जो पहले रिजेक्ट थी, और रिजेक्ट के बाहर भी कोई ट्रांजिशन मत करो. एंड फॉर ईच कॉम्बिनेशन ऑफ नॉन एक्सेप्टिंग स्टेट ऑफ एम on input and tape symbol of M, you have to see that M has no transition and M halts without accepting for and add a transition to the accepting state R. इसका मतलब ये है कि accept में it will halt without accepting and state R तक transition करो for create ये non accepting states के लिए आप ट्रांजिशंस करो विदाउट एक्सेप्टिंग, एंड आर के लिए पहले जो रिजेक्ट था उसके लिए आप एक ट्रांजिशन करो सो दैट इट बिकम्स एक्सेप्टेड. सो एम प्राइम विल एक्सेप्ट द स्ट्रिंग्स which were not originally accepted by M, and it will reject the strings which were originally accepted by M. I think this is pretty intuitive. इसमें इतना कुछ सोचने वाला नहीं है. Okay, if a language L and its complement are recursively enumerable, then L is recursive and so is L prime. अगर language L और उसके complement recursively enumerable हैं, then वो खुद recursive है. मतलब अगर एक language है, मैं अभी आपके पास यहाँ पे recursive language है एंड आपके पास यहाँ पे एक रिकर्सिवली एन्यूमरेबल लैंग्वेज है, ठीक है, ये लैंग्वेजेस का सेट है। अगर एल और एल प्राइम दोनों इस सेट में है, इसका मतलब आप इनको इस सेट में डाल सकते हो। वो क्यों होगा? अगर आप इन दोनों को देखो, एल क्या है, एल इज बेसिकली इसकी अगर आप ट्यूरिंग मशीन एम एल बनाओगे तो इट इज गोइंग टू एक्सेप्ट certain strings and we don't know what is going to happen for the strings that are not there in L. But L prime में क्या होने वाला है? It is going to accept those strings that are not here. वो यहाँ एक्सेप्ट हो जाएगा। जो यहाँ है, जो यहाँ है, उनका क्या हो रहा है इसको नहीं पता। बट अगर मैं इन दोनों की पावर को कंबाइन कर दूं, अगर मैं इन दोनों को जोड़ दूं, तो मेरे पास डिसीजन आ जाएगा। इस केस में यहाँ एक्सेप्ट करा दो, रिजेक्शन के केस में यहाँ एक्सेप्ट करा दो, तो डिसीजन तो आ ही रहा है ना, हॉल्टिंग तो हो ही रही है। तो इसलिए दोनों को कंबाइन करके हम रिकर्सिव में डाल सकते हैं। तो फॉर्मल प्रूफ यहाँ पे लिखा हुआ है, बुक में लिखा है, तो आप वहां से देख लेना। बट दिस इज एन आइडिया, जस्ट कंबाइन एंड जो एक्सेप्ट कर रहे हैं उनको एक्सेप्ट करा दो। जो M2 या L प्राइम वाली ट्यूरिंग मशीन है, वो जो एक्सेप्ट कर रही है वो फाइनली रिजेक्ट करेगी क्योंकि L की बात हो रही है। सो अगर L प्राइम करना होता तो यहाँ पे रिजेक्ट लिख देते और यहाँ पे एक्सेप्ट लिख देते, तो वो इसकी ट्यूरिंग मशीन नहीं है। आई थिंक दिस इज प्रिटी सिंपल, इसमें इतना सोचने वाला नहीं है। स्टिल देयर इज अ डाउट एंड आई कैन आंसर इफ यू वांट टू आस्क। Okay, all this is what we have already discussed. I think I have pasted the proof here. So I think this I think you can do on your own. Okay, so complements of recursive and recursively enumerable language. So let me write recursive, then recursively enumerable and not RE also. Okay, तो देखो बहुत सारे कॉम्बिनेशंस हैं कि L और L प्राइम यहाँ हो, L यहाँ हो, L प्राइम यहाँ हो, L और L प्राइम दोनों यहाँ हो, जो हमने अभी प्रूव कर दिया कि वो वापस इधर ला सकते हैं। दूसरा है कि L यहाँ हो, L प्राइम यहाँ हो, और ये हो सकता है L यहाँ हो, L प्राइम यहाँ हो। एक और ऑप्शन हो सकता है कि L प्राइम यहाँ हो एंड L यहाँ हो, या L prime यहाँ हो और L यहाँ हो. So there are a lot of combinations that are possible, but only few of them hold. So we are going to talk about them. बना के एक बार देख लेना. So they are saying that only these holds. Out of the 4 possibilities for placing L and N prime, only 4 are valid. One is L and L prime are recursive, that we have already done. Neither L nor L prime is RE. मतलब यहाँ पे भी नहीं है, यहाँ है, दोनों यहाँ है. L is in RE but not recursive, so L is here, and L prime is not in RE, rather L prime is here, this combination. And L is RE but not recursive, L prime, and this I have already discussed. L is RE, not recursive, and L prime is not in RE. And बेसिकली ये बोल रहा है कि एक जो है मिडल रिंग में है और एक आउटर रिंग में, मतलब L प्राइम या फिर L प्राइम L, ऐसा. And L prime is RE but not recursive, and L is not in recursively enumerable. सेम चीज जो मैंने अभी बोली है. तो ये 4 कंडीशंस हैं जिसमें से आई थिंक हमने ये वाली तो प्रूव कर ही दी है that LR and L prime are both recursive. So let's see what is happening. ये सेम चीज आई थिंक जो मैंने अभी ड्रॉ करके बनाई है. Okay, so this is what we were talking about right now, and LD is not recursively enumerable, that we have already shown because there was no TM that we could build. So LD prime cannot be recursive क्योंकि वो उन 4 cases में नहीं आ रहा. So that means LD, अगर LD is that's why LD prime is recursively enumerable. It cannot be recursive क्योंकि वो ये वाले cases में नहीं आ रहा. So which is saying that it is LD prime के लिए भी okay. So LD के लिए कोई ट्यूरिंग मशीन नहीं है, and it contains all words such that the Turing machine does not accept the encoding. Now they are saying that LD prime is recursively enumerable. इसका मतलब there is a Turing machine, and for those words that are in LD, it is going to halt. So LD prime is a set of strings WI such that MI accepts WI. This is language similar to LU, so we will be using LU in the next slides, and you can use the same argument for LD prime also for showing LD prime is recursively enumerable. Let me come to that soon. So it is landing up here. LD is here, not recursively enumerable also. So there is no TM for these languages. And there is a Turing machine for this language which halts on the words in LD prime. What happens to other words? It is not going to say anything. So LD prime is recursively enumerable but not recursive. So because it is not recursive, so it is undecidable. Anything that is not recursive is undecidable. So although there is a TM for LD prime, it is still undecidable because you don't know what is going to happen if the word does not belong. Now the next thing, which is LU, the UTM, is also it also has the same property that it is recursively enumerable. So whatever logic you are going to use for LU, you can use for LD prime also. Okay, so the universal language LU is the set of binary strings, each of which encodes जो भी आपने ट्यूरिंग मशीन की नोटेशन बनाई थी, तो ये एक ऐसी ट्यूरिंग मशीन है जो सारी ट्यूरिंग मशीन एक्सेप्ट करती है. तो इट सच दैट W इज इन LM, मतलब हर ट्यूरिंग मशीन की जो एनकोडिंग है WI, वो LU का पार्ट है. यूनिवर्सल ट्यूरिंग मशीन, एज द नेम सजेस्ट, it is going to accept all the encodings in 0 plus 1 star, and all these encodings are encodings of Turing machines themselves. And LD prime क्या था? Strength of strings WI such that corresponding MI accepts WI. तो similar है. LD is MI accepts WI, and LU prime LU is something that MI accepts WI where WI is the encoding. So the definition is similar. Here WI is a string And yes, so here wi is the string of the Turing machine, and lu में भी जो wi है वो string of Turing machine है. So they mean basically the same thing. So it can be shown that there is a TMU universal Turing machine which accepts LU, and L of U is the language LU. So you have to construct a multi-tape TM. Remember, I had already talked about a multi-tape TM जिसमें एक टेप पे आप इनपुट लेते थे, एक टेप पे आप ट्यूरिंग मशीन के ट्रांजिशंस लेते थे, एक आप एज अ बफर यूज कर लेते थे. ऐसे बहुत सारे टेप्स आप बनाते थे. इसको अगर सिमुलेट करना होता तो आप सिंगल टेप में भी सिमुलेट कर लेते, वेयर some sides represented this, you had left some blanks in between, and then this blank, some portion blank, and then the third tape on this side. So single tape की तरह भी simulate किया जा सकता था. तो हम multi tape TM simulate करेंगे, but it can be imagined to be implemented by a single standard Turing machine also. So how we are going to make this run? LU is a recursively enumerable language. See, ये क्यों बनाना है? क्योंकि हम ये प्रूव करें कि इसके लिए ट्यूरिंग मशीन एग्जिस्ट करती है. तो ट्यूरिंग मशीन जब एग्जिस्ट करती है तो हम ये बता सकते हैं कि वी आर एटलीस्ट हैविंग समथिंग व्हिच इज एक्सेप्टेंस. जस्ट अ सेकंड, आई हैव गॉट अ कॉल प्लीज. जस्ट अ सेकंड, आई हैव गॉट अ कॉल. सो यू हैव मल्टी-टेप ट्यूरिंग मशीन. फर्स्ट टेप पे इनपुट है m, w, मतलब आपने एनकोडिंग ऑफ m रखी है यहाँ पे. सेकेंड टेप पे आपने टेप ऑफ m रखा है, मतलब बेसिकली इनपुट जो भी होता पास करोगे, इनपुट टेप ऑफ m. ये ट्यूरिंग मशीन m है और ये उसकी एनकोडिंग है. तो फर्स्ट पे आपने ट्यूरिंग मशीन रखी है, क्योंकि यूनिवर्सल ट्यूरिंग मशीन क्या है? जो वो वाली ट्यूरिंग मशीन है और जो ट्यूरिंग मशीन्स अपने आप को एक्सेप्ट करती हैं उनके लैंग्वेज है. सो यहाँ पे एनकोडिंग्स रखी. आप ये एक्चुअल ट्यूरिंग मशीन जो जो आप भी पास कर रहे हो उसका टेप रखा. यहाँ पे आपने ट्रांजिशन, स्टेट ट्रांजिशन रखे और ये स्क्रैच टेप है अगर आपने कुछ प्लेस करना है, कॉपी करना है उसके लिए. सो इसमें कुछ नहीं बोल रहा. लेट मी जस्ट ड्रॉ these tapes again. Here you have encoding, and here you have tape of m, and then you have, let me draw it here, the transitions, the state transitions, and then here you have some scratch tape to keep it as a temporary buffer or something. So इसको कैसे बनाओगे? Transitions of m are initially stored in first tape. Second tape will be used to hold the simulated tape of and the tape symbol xi of m will be represented by 0i, जैसे आपके xi 0j वो सब होते थे. And tape symbols will be separated by single ones. तो जब आप क्योंकि ये टेप है तो आपको, अगर आपको याद होगा तो आप ये 0j और 0k से टेप सिंबल्स बताते थे, और 0i एंड आई थिंक सॉरी j एंड l से आप टेप बताते थे, एंड 0i एंड 0k वर योर स्टेट्स. तो स्टेट्स यहाँ पे आएंगी इस फॉर्म में, समथिंग ऑफ लाइक 0 0 एंड 0 0 0, एंड टेप पे ये वाले आएंगे 0i एंड 0j एंड 0l. तो वो एक सेम सिमुलेशन है. अगर सेपरेटर्स यूज करने हैं तो 111 लगा देगा. तो यहाँ पे जो भी डालोगे 0 0, फिर सेपरेटर के लिए 111 लगा देगा, एंड 0 0 whatever. So the holds a state which I have already told you is of this form. So you have to examine the input to make sure that the code of M is legitimate. If it is not legitimate, it only has one state and it will accept no input and it will halt without accepting. So initialize the second tape to contain the input. Again, let me draw this. फर्स्ट स्टेप में एनकोडिंग है, सेकेंड टेप में वही जीरो आई सॉरी जीरो जे जीरो के फॉर्म में. ये देखो यहाँ पे स्टेट्स थी, दिस वाज स्टेट्स एंड दिस वाज व्हाट यू रोट ऑन टेप. तो इस टाइप के जो फॉर्म के स्ट्रिंग्स हैं वो यहाँ जाएंगे टेप 2 पे, और ये जो स्टेट्स वाले हैं, the state ones will go here, and then you have a buffer also. I hope that buffer is visible. Anyways, I'm not going to use it now. So it is simply saying that second tape को input डाल दो, जो ये वाला input है सिर्फ ये डालो, बाकी सब नहीं, input डालो, and separate कर दो by placing a 1. Blanks are simulated by this. हो सकता है कि they do not appear on the tape and they appear as blanks over here. So we are not concerned with that, how it is going to use them. And it is going to just interpret this tape symbol which is written something like this. So place 0 the start state of M on third step. ये वाला जो है ना start state, वो पहले यहाँ पे रखो. अब देखो जब भी ये स्टेट पढ़ोगे यहाँ पे तो कुछ एक्शन होगा तो स्टेट चेंज हो जाएगी, मान लो 0 0 हो गई, और हो सकता है कि टेप पे भी कुछ चेंज हो जाए, मान लो सिंपल ये हो गया. तो अगर हम ये बोल रहे हैं कि यहाँ से इस स्टेट पे मूव करो तो वो ये यहाँ पे सिमुलेट होगा, एंड टेप पे ये इनपुट था, अब टेप पे ये आउटपुट आएगा तो वो यहाँ मूव होगा. तो ये सारी कहानी उसने यही लिखी है. Change the contents of tape 3 to simulate the state change and replace the 0J by 0L to replace the tape symbol, and then move the head. आपका initially head यहाँ था, अब इस हेड को यहाँ मूव कर दो, तो आपने सिमुलेट कर दी UTM on a multi-tape machine, and you can use it to use it in as a standard Turing machine also. So same है, and बाकी फिर steps they will go on, and कोई transition नहीं है तो वो halt कर जाएगा, and you have it accepts the coded pair NW. If the word does not belong to the language, we are not talking about it. So that's why this is recursively enumerable. So why we have done all this again? Because आपको TM U को RE बता देता था. ये रिकर्सिवली एन्यूमरेबल थी बट अनडिसाइडेबल थी. अनडिसाइडेबल मतलब कि एक्सेप्ट तो हो रही थी क्योंकि मैं टीएम बना पा रही थी इसकी, तो एक्सेप्ट हो रही है, बट अगर कोई वर्ड लैंग्वेज में नहीं आ रहा तो क्या हो रहा है, आई डोंट नो. ओके, सो ये यूटीएम की कहानी हो गई. So I have an option of stopping now and starting tomorrow. What else is there? There are a lot of things to be covered still. Okay. So I think I will leave you to this today. Tomorrow I am going to talk about what? Okay, tomorrow I will be talking about undecidability of UTM, which I think let me cover this at least. Undecidability of UTM. And then tomorrow I will start with halting problem. Okay, let's finish this off first. We have time at hand, right? Time. Only 10, right? Okay. Okay. So we are saying that LU is recursively enumerable, but it is not recursive. We know LU is recursively enumerable because we have constructed a Turing machine for it. Now let's assume that LU is recursive. So अगर LU रिकर्सिव है तो LU प्राइम भी रिकर्सिव होगा, वो हमने ऑलरेडी डिस्कस किया हुआ है. सो मतलब LU इज डिसाइडेबल, तो उसके ऑपोजिट जो वर्ड्स एक्सेप्ट नहीं होते हैं वो भी रिकर्सिव होंगे. So we can create a Turing machine M to create LU prime. So but this is contradictory क्योंकि LU prime is exactly LD. LU is what? All those ट्यूरिंग मशीन्स जो अपनी एनकोडिंग को एक्सेप्ट कर रहे थे, और एलडी क्या थी? ऑल दोस ट्यूरिंग मशीन जो अपनी एनकोडिंग को एक्सेप्ट नहीं कर रहे थे. अब अगर हम एलयू को रिकर्सिव बोल रहे हैं, और हमने थ्योरम पढ़ी है कि अगर एक रिकर्सिव है तो दूसरी भी रिकर्सिव होएगी, क्योंकि हम उसके एक्सेप्ट स्टेट्स को कंबाइन कर सकते हैं. इसका मतलब कि एलडी भी रिकर्सिव हो जाएगी, which is we have already proven not recursively enumerable. So our assumption is wrong. That's why LU is not recursively LU is recursively enumerable but not recursive. So let's not get into these reductions. I will tell you later. So undecidability is you have to construct M prime like this. Let's assume it is uh, recursive. So you have a word that you have to pass, and you are creating a hypothetical M. You are passing a copied string to it, and it is going to accept or it is going to reject. Just a second. So much noise. So you are going to create a hypothetical Turing machine and say that because it is recursive, so it has to have something for accept and some reject state also. So let M be a Turing machine such that it accepts LU prime, and if it accepts LU prime, then it will accept LD. That means that each input pair M is a pair of MI WI, where MI is the code of Turing machine and W is the binary input string. So MI का code और WI जो string आप MI को दे रहे हो वो. Also note that each input into M prime is the code of Turing machine because M prime accepts LD. Each input into M prime is the code of Turing machine because हम ये मान के चल रहे हैं कि M prime जो है diagonalization language को accept करती है. I personally feel that proving diagonalization language is not recursively enumerable should be enough and not going into all this. But okay, let's see this approach also. So given input string, आपके पास एक ट्यूरिंग मशीन आप हाइपोथेटिकल बना रहे हो, इसके अंदर आप M, W पास कर रहे हो, where W is the input for this machine, जो आपने अभी कॉपिंग मशीन बनाई थी, उन्होंने वो बना के देखी है, और एनकोडिंग ये ऐसा है, and encoding of this. So given input binary string W, M prime will have to change this to a copy of this. So which means the pair M prime prime W, where M prime is the TM encoded by W. So you can do this. So basically ये जो ट्यूरिंग मशीन है वो कौन कर रहा है? वो एक कॉपिंग मशीन कर रही है. अगर हम वापस जाके देखें तो आपने एक स्ट्रिंग पास करना है W, और यहाँ W पास करना है विच इज फॉर हाइपोथेटिकल LU प्राइम. बट वो किसके लिए है? LU प्राइम के लिए, वो मशीन M के लिए है. और M को आप क्या पास कर रहे हो? W पास कर रहे हो. अब आप ये बोल रहे हो कि ये W जो है बेसिकली सिमुलेट हो रहा है बाय गेटिंग कॉपीड फ्रॉम दिस. सो given input binary string W, M prime, the original machine जो आप पास करा रहे हो, it changes to this, which means that it is being done by a TM called copy. So if W into M prime is WI representing MI in the TM list, अगर जो भी आप W पास कर रहे हो M prime को, वो एक WI है which is representing the MI, तो जो कॉपी मशीन आपको प्रोड्यूस सिमुलेट करके दे रही है वो 2 कॉपीज है ट्यूरिंग मशीन MI की, जो कि एनकोडिंग है इसके M के. If and only if MI does not accept WI. This is in turn means M prime accepts M prime only if MI does not accept WI. So which is kind of which we are saying कि WI आपने इनिशियल कॉपी मशीन को पास ऑन किया, तो ये बेसिकली ओरिजिनल मशीन थी MI जिसको आपने WI पास किया, जिसका रिजल्ट ये था. आपने उसको हाइपोथेटिकल LU प्राइम की मशीन पे पास किया and it is going to accept if and only if MI does not accept WI and M prime accepts WI only if MI does not accept WI because आप LD prime की बात कर रहे थे. So in that case this is something that for this been copied from somewhere. This is not possible. It's a contradiction. So LD is not a recursively enumerable language that we have already said. Okay, I think this might not be clear today, so maybe let me repeat it tomorrow. I will repeat this portion tomorrow. Till then, just give a read to. Then we are only left with the halting problem definition and the reductions. So I will try to finish this off tomorrow. Okay, I will repeat the one I have done right now tomorrow. Anyone, if before this universal Turing machine ka proof, anyone if has any problem, let me know. Otherwise, you can exit the class.